Greener MOF processing cuts costs for water treatment plants. Metal organic frameworks, MOFs, are highly porous materials made from metal ions linked by organic molecules. Their large internal surface area allows them to capture selected contaminants, including heavy metals, from water. A new study published in Green Chemistry focuses on a practical challenge facing MOF-based water treatment: manufacturing cost. While MOFs can provide highly porous structures capable of binding selected contaminants, their production can require significant energy and solvents. There are also concerns that some materials could release constituent metals during use. University of Birmingham researchers have been working to reduce those barriers by developing both the material and its manufacturing process around green chemistry principles. Their latest findings suggest that changing the post-processing stage could reduce resource use without substantially compromising lead removal performance. Freeze-drying cuts estimated energy use and production costs. The team previously developed a water-based manufacturing process for MOF intended to recover heavy metals and rare earth elements from industrial waste streams. A patent application covering the material and production method has been filed by University of Birmingham Enterprise. In the latest study, researchers replaced the previous post-processing approach with freeze-drying. At laboratory scale, the change increased the amount of usable material recovered by more than 3 times. Estimated electricity demand per gram fell by around 74%, while calculated production costs dropped from approximately $19 per gram to just over $5 per gram. Those figures should not be treated as commercial pricing. They are based on laboratory-scale production, and costs could change substantially as the process moves into larger manufacturing environments. Reductions in both material losses and electricity requirements, however, could help address 2 of the issues that have limited the commercial case for advanced adsorbent materials. For water treatment operators, manufacturing economics will need to sit alongside factors such as contaminant selectivity, regeneration, service life, and the cost of treating each unit of wastewater. The format of the material could also support industrial handling. Rather than being produced as a fine powder, the Birmingham MOF is formed into pellets, which may simplify its recovery and use within treatment systems. Lead removal performance points to next phase of testing. The change in processing did not appear to remove the MOF's ability to capture lead. Testing showed more than 90% lead removal during the first hour, with high removal levels maintained across 4 consecutive treatment batches. Researchers also assessed the material after 7 days of exposure to air, freshwater-like conditions, and artificial seawater. It retained its main structural characteristics across those environments. Earlier testing using real-world water samples containing mixtures of contaminants also found strong lead removal alongside relatively low copper leaching. Limiting such leaching is important because an adsorbent that releases its own metals could create additional treatment requirements. Potential applications include wastewater generated by mining, electronics manufacturing, e-waste processing, and chemical production. In some cases, selective capture could also support the recovery of metals with commercial value rather than treating them solely as waste. Significant questions remain before the technology can be assessed for routine industrial deployment. Wastewater chemistry can vary between sites and processes, while treatment materials may need to withstand repeated regeneration cycles and prolonged exposure to challenging operating conditions. The Birmingham researchers are seeking partners in mining, e-waste, and water treatment for licensing and pilot-scale testing. Those projects could provide a clearer indication of whether the lower energy manufacturing approach can translate from laboratory economics into a viable industrial water treatment process.